and then go to work at ATK. He's going to be telling us about what his inspection of materials that he's going to be doing at ATK. And he told me that if he could be anyone, he would choose to be MacGyver. Which, actually, I think MacGyver could perhaps have used some materials in safety inspection, so he's helping out with that. So let us welcome our speaker, Ian Cox.
For starters, I won't be offended if anybody wants to come down and grab more treats during the talk. Just do it quietly and noted. Fine. The attention grabber up here is an airplane. This is the Strato launch, where ATK, who I'm working for currently, is building one of the first rocket motor stages for this. The plane itself is longer, has a larger wingspan than any other plane that's ever been built. It has more power than any plane that's ever been built. You have 6 engines, 3 on either side. If we were to ignite our first stage on takeoff, it would have the thrust-to-weight ratio of an F-16. But the goal of this plane is to get rockets or other space missions up into orbit without having to send them straight up and get them up first and launch the rocket. So that was the interesting thing to get you guys to come to the seminar, which won't be terribly relevant to anything I'm about to say. My background, I'm currently studying applied physics at Weber State University, as most people here know. I did some research with the Harbor team and went on lots of excursions with them out into the desert. And I can pretty much say that my experience with Harbor is the reason I got my job at ATK. Beyond my physics knowledge, having that hands-on experience heavily weighed in my favor compared to the other candidates, because they want to hire somebody with a little bit of blood on their hands. If you just have a purely theoretical background, you've never done anything with it, then you might as well just do some research at school and then get a job. So if you have the opportunity, get involved with undergraduate research. Every single professor in this department is doing something cool, and if they're not, you can tell them what you want to do and they'll help you do it. So I strongly encourage getting involved. And now I work at ATK as an inspection systems development intern. What we do is we develop methods to inspect these parts, and I'll talk all about that. So first of all, why do we need to inspect things in the first place, and why do we choose ultrasonics? The carbon fiber composites that we're dealing with are made, if you came to Ken's talk, who's sitting in the back up there, you kind of got a taste for how they're made. You can either have the individual carbon fibers wound piece by piece, strand by strand, or you can have pre-impregnated layers of carbon fiber that are put down layer on top of one another. And this process is typically happening very fast, and oftentimes, if you want to be inspecting it as it's being made, you can't get in there, you can't get a camera, you can't get an operator, you can't scan it while it's being made. So we wait until the part is completed, and then do a complete inspection afterwards to ensure quality. It's non-destructive, which is a big benefit. If you're making pencils, let's say you grab 1 out of every 1,000 pencils you make, and you test it, you break it, say, okay, well, we'll assume that those other 1,000 that were made that day are still good. With airplane parts and rocket motors, you don't want to test 1 out of every 100,000 that you make or anything like that. So this gives you a non-destructive way to inspect every part that goes out the door to ensure quality, make sure nobody's going to die, which is a good thing. What we're looking for, a couple things: foreign objects or debris or damage. Anything that can get into the material while you're making it. This can be plastics, tapes, razor blade tips, fingernails, anything that you wouldn't want getting sandwiched between 2 layers of composite material, because once you put it into an aircraft, it might start vibrating. It could burn a hole through the aircraft. It could do all kinds of different things. You can also have flaw. You can have areas where the composite isn't actually adhered to the layer beneath it. We call it a delamination. So anywhere where you have a void, kind of an air pocket, or a part where it's just not adhered right, that will start to vibrate once you excite different vibrational modes in the material. Flaws, any cracks, things that we're looking for. And then also failure analysis. What we can do is if we build a part, you can scan it, then you can do something to it. You can break it, you can smack it, you can bend it, and then scan it again afterwards and see what changed. And as far as scanning, you'll get a little bit more of a feel for what I mean by that as we proceed. And failure analysis, if something were to fail, we can go through it afterwards and scan it and see, okay, what was likely to have caused this to fail. So, now, you go into traditional methods. You can visually inspect parts, or you can tap. And what tapping is, you just take a coin or a hammer, and you go around, and you knock, and you listen. And it's like finding a stud in a wall. You're listening for that change in whatever's behind the material. So if you have a hole, all of a sudden hear a hollow spot. Now, this is a perfectly valid method. You can use it. You can inspect an entire part. But you can imagine an entire rocket motor would be tedious to go every single centimeter and go along and tap it. And it might be more cost effective to scan the whole thing depending on how much you're paying the guy to tap the point. But another downside is the size of flaw that you can detect. If you had a little 2 millimeter flaw in there and you were tapping to try and hear for it, you might not be able to resolve that. But with ultrasonic waves with high frequency, it could be clear as day. There's a hole right there, whereas with a coin tap, it could be harder. So we use ultrasonics to more efficiently inspect these materials. So we're going to be talking about waves, sound waves, ultrasonics, same thing. The reason it's ultra is that it's above the range of human hearing. You have the acoustic range, infrasound, and ultrasound, where ultrasound is things that we can't hear. Now, when waves propagate through materials, you know you can have atomic level vibrations. You can have the atoms stretching, twisting, bending, all these different modes. But that's not what we're concerned about. We're concerned about the mechanical vibrations of the system as a whole. Large particles in bulk motion moving together. So this is, if you've ever seen, you can take like a violin bow and you saw it on the side of a metal plate, and you can excite different modes. These are some really cool ones that were excited electrically, not with just a violin bow. But you put sand on the plate and you can see that the plate itself is fluctuating and not just the atoms in between. Right, so ultrasonics focus on those vibrations, sound waves traveling through media. Now, sound waves are the reason you guys can hear me right now, but we know that they behave in a specific manner. Sound waves sent out will propagate predictably, and when it reaches a boundary, an interference, anything, it will reflect, refract, transmit according to rules that we all kind of are familiar with. It's a little different for materials than it is for, let's say, a perfect glass optical surface, even though that's not even perfect. But there are more things going on with composite materials because you have layers. The wave propagates differently in different directions, which we'll talk about also. So if you send a sound wave into material, you're monitoring the pattern of the echoes, right? You see what's reflecting off of what, and you're seeing how that changes as you scan the entire part. So if that sound wave goes in and reaches a crack or something foreign, there will be an impedance mismatch there between the two layers, and you get a reflection off of it, and you can detect that. Get into that also. This is all the over. So, here's what I was talking about: acoustic, ultrasound, infrasound. Note that this is a logarithmic scale, not linear, so to give you an idea of where those frequencies fall relative to things you're comfortable with. There you go. Note that it says that medical ultrasound is destructive, but no, you're not destroying babies when you're getting an ultrasound. So that's destructive testing and medical ultrasonics, two different fields that fall around the same frequency. With a higher frequency, you get higher fidelity. What does that mean? So let's say we send in a waveform and we get something like this, beautiful wave. That doesn't carry much information compared to something that comes out looking like this. So if we're using a higher frequency, you get a better fidelity. You're able to resolve smaller differences in your waveforms than a lower frequency. But the catch is that lower frequencies attenuate less in the material. What attenuation means is your signal loss, amplitude. So if you have a material use a really low frequency, those waves propagate through more efficiently. Think of when you have a rock band next door to you, you hear those bass notes, you hear the bass drum coming through your walls, but you don't hear the higher stuff because those low frequencies are able to transmit through the media more efficiently. So you have to kind of play a game and pick your frequencies accordingly. How high do you want the frequency to be so you can see the things you want to without losing your signal? So for carbon composites, a typical frequency range, just for context, is 1 to 15 megahertz. Cool. Any questions so far? Feel free to interrupt and raise your hands. Yes?
Chemistry sound? Animals and chemistry?
Animals and chemistry. Ultrasonics used in chemistry. I pulled this graph off of Wikipedia. But imagine animals can hear in that range. Chemistry, since you're a chemist, you would ask the question.
So
I imagine
here go on?
they can. Yeah, anybody who has a degree in chemistry. I imagine
I learn something new every day.
all your ultrasonic shakers that you might use for testing. Have you used any of those up there? No? Cleaning?
Sonication.
Sonication, that's ultrasound, right?
Yeah.
So maybe the frequencies, Dr. Stoll, thank you.
You can change surface chemistry will behave differently with ultrasonics. That's what an ultrasonic cleaner does. It breaks up surface tension to allow better chemical contact and drive chemical processing.
Thank you.
Thank you.
Are you talking both longitudinal and transverse?
We'll be getting into that momentarily, I believe. Maybe even right now. So, good segue. Thank you. You know where I'm going.
Wait, is there a question back there?
Yes, it's out.
Green shirt, Oakley?
Why were the arrows pointing down at the line?
Because this goes on forever in both directions, so the line extends. Oh, that line. Oh, this tells you where these are located. So they're somewhere between 2 and 200. You see the big numbers up top? So this one falls down in here. That's where that one is. Thanks, Oakley. So modes of sound waves. I assume all of us are familiar with the high mode, the high wave, the low wave, and the bro wave. We all know those wave modes, but who all is familiar with longitudinal transverse waves? Dr. Galley's already stated it. Students, you've had exposure to these before. What about the other ones? Surface waves, guided waves, plate waves. Any of those, you've touched on them? Okay, well, we'll get into those right now, actually. So we'll start longitudinal transverse. These, I brought this lovely demonstration here. Your longitudinal wave, nice, it's a compression wave that travels where your particle motion is in the direction of wave propagation. So the waves are propagating here, your particles, if you were to pick one single band of this slinky and watch it, it's oscillating in the direction of particle motion, right? Now, transverse waves, the particles are oscillating perpendicular to the direction of wave propagation. If you were to pick any single one, it would be doing this as the wave travels in this direction. And so longitudinal waves are sometimes called pressure waves and compression waves because the material is compressing, you're sending a compressional force down onto it. And also they're called density waves because the local density in the material is fluctuating as that material gets compressed. Very small amounts, but this is kind of a macroscopic view. So transverse are also called shear waves because that's your shear mode as the particles are oscillating in that direction, right? So fun fact, the definition of a fluid is any material that can't support a shear, right? So you have, with zero frequency, correct? Yeah, so waters, air, anything you define to be a fluid can't support a shear. So now we'll get on to the next part with some cool animations. Surface waves are a longitudinal compression wave excited at an angle. The goal is to get the wave to travel along the surface. Now you can have material that's as thick as you want, but the particle motion will be localized to only the surface. You can see up here the particles, if you follow one of these trace particles, following an elliptical path, right? But the ellipse up here that this particle is tracing out is larger than this one, larger than this one. It decreases as you go through the depth of the material. Everything down here is stationary. Notice also that the larger axis of the ellipse is perpendicular to the direction of wave propagation. It's not at some funky angle. This will be perpendicular. Now, how do you get one of these surface waves? I told you it's a longitudinal wave excited at an angle, but that angle is kind of critical. If we go to have material here, and we have Snell's law, right? You guys know that. You have your incident angle, and you'll have some refractive, where here you have the speed of sound. Let's say this is water. Down here you have whatever material you have. But this isn't actually entirely true because in the material, like I said, you have the sound velocity is different for different directions. You'll have a transverse velocity and a longitudinal velocity. So that'll actually go through what we call a mode conversion and split, and you'll have two waves then propagating through. So this should probably be a longitudinal transverse. The goal is to get your transverse up so that it's propagating along the surface, right? Because you want to excite a surface wave. So you have to find an angle such that your, let's call this theta transverse, is equal to pi halves or 90 degrees, so that you're then sending a wave propagating along the surface of the material. So that's what's called the critical angle. I think they actually call it the third critical angle. I don't know what the first and second are. The critical angle to excite surface waves. But that being said, you don't need to know that to detect them. Anytime you hit a material with something, eventually a surface wave will propagate. You might not be able to detect it right away because it'll be bouncing around, but sooner or later, every time it hits a surface here, we'll be going through mode conversion, mode conversion, mode conversion. And also, when this sound wave comes in, it's not just a line, you have a wave front coming in, right? So you have multiple angles hitting that surface and then bouncing off every time. So sooner or later, you're going to get a surface wave excited. So those are surface waves. They're nice because you can detect them. They travel on the surface, so you can look for flaws near surface, and they also can travel around contours, things that aren't necessarily geometrically perfect for what you're trying to do. So you can have an impact over here and then pick it up somewhere else, even if there's a curved contour. Leaky Rayleigh waves, oh yes, I did put those up there. Leaky Rayleighs are what kind of come out of the surface wave. So you have the surface wave, all that energy won't be contained within the surface, it's going to be sending waves in both directions every time. So if you were to have something submerged, you'd be able to detect the leaky Rayleighs as they come off the surface. Rayleigh waves are a theoretical impossibility. Mr. Rayleigh derived them assuming a quasi-infinite material where it's infinite in all of these directions other than the surface that you're interested in. So it's not, if it were infinite everywhere, it'd be kind of hard to have a surface. But it's a quasi-infinite material, and so since Rayleigh's the theoretical physicist that came up with it, it's a theoretical impossibility. SAW waves are, surface acoustic waves, are the actual physical thing that you can detect. So SAW waves are to Dr. Inglefield and Dr. Soul as Rayleigh waves are to the rest of the department. Dr. Carroll's over there meditating on Venus in his mind. He's so theoretical. So, SAW waves. Plate waves are similar to Rayleigh waves, but they can only be generated in a material that's a few wavelengths thick, an actual plate of material. And wavelengths here depend on the sound velocity in your material and the frequency you're choosing to inspect it with. Previously on the slide beforehand, surface waves usually travel at a depth about 1 wavelength thick. Just for reference, whatever you want. About 3 millimeters for our cases if we do some math, which I could do for you, but you all know how sound and time and velocity work. Did I talk about this yet? Oh, no, I didn't. Love waves and Lamb waves are 2 types of plate waves. So if your particle motion is in this direction, they both oscillate perpendicular to the direction of wave propagation. But the difference is that love waves are parallel to your surface, so they're going in and out of the board this way. If there's your y, they're traveling your y-axis. Lamb waves are orthogonal to your surface, but still perpendicular, well, still orthogonal to the direction of wave propagation. So within those plate waves, you have 2 modes of symmetry, antisymmetrical and flexural. So we can think about these. You guys have probably seen these before. Is that easier up there? I don't quite know. If the dashed lines are your surfaces at their resting position, that would be an antisymmetric wave mode, and this would be a symmetric wave mode. And a nice way to think about this is if you had, let's say, an aluminum rod and you start shaking it, you would excite, the whole thing would kind of wiggle in this direction, right? So that would be your flexural mode, your antisymmetrical mode. Both the surfaces are kind of moving in conjunction with one another. Then if you were to take that rod and smack the end of it with a hammer, what would happen? You'd send a compressional wave down the rod, but what's happening to the diameter along that? It's fluctuating in this direction, so the surface then is doing this as that wave propagates down. So those are your 2 different modes you can have with plate waves. For our purposes, I don't think this is true entirely, but the flexural mode tends to have a lower frequency, lower velocity, and travels further with less attenuation. So we typically are picking up the flexural modes when we're looking at plate waves, and not necessarily the extensional modes. Any questions there? Cool. So an application of plate waves, this is the CCM, this is the composite crew module. This was built for Ares 1, which I believe was the last proposed manned mission to anywhere. And then the funding got cut, and now we have SLS. But this was the crew containment module, or composite crew module. You'd have 3 women or men, whoever ends up going up there, inside of this thing. Here's a generic man for reference of size. And it should be noted also that this is your floor. So all those people would be contained in there for however long it takes to get to Mars or wherever they were planning to go. But we designed, well, not myself, there was a system designed where you have, right here, this is an array of ultrasonic detectors. I'll explain more about those, but for now I'll just say a collection of ultrasonic detectors here, there, all around the case, so that while the part was being transported, if it were going to get knocked by something, if somebody was throwing a big strap over it to tie it down and got impacted, that would excite a plate wave, which would then be detected, sent to a laptop or a phone or whatever you want to say, hey, there was an impact, there might be damage to the case. But the cool thing is, not only do you know that that happened, you can triangulate based on your time of flight and how those waves arrive at that little array and all the other ones, and say, okay, this is where the damage is. We need to start looking in this area. So that's a useful application of plate waves. So, transducers. These are the ultrasonic sensors and transmitters I was discussing. Basically, the idea is to take an electric signal and transmit it into a mechanical vibration. Now, the way that happens is pretty cool. Is Dr. Schroeder here? Oh, you'd be so proud. Okay, here we go. So, let's say we have a dielectric material. I assume for everybody who's taken Physics 2220 and above, you have experience with this. For everyone else, it's just an insulating material. I think we only call it a dielectric when it's between two plates of charge. Other than that, it's just an insulator, but it's the same idea. So we put a plate, and a metal plate on either side, and inside here, we'll have just a bunch of dipoles. They'll be randomly oriented, not polarized, because the dielectric material is polarizable, but not necessarily always polarized. So that's how it kind of biased. That's how it is at rest, right? Kind of random distribution there. Now all of a sudden, let's say, actually I'll draw it over here. Or here. Open switch. Now we come over here, and we put a current onto that dielectric material, or across that dielectric material. So now that's connected. We have, let's say we have negative here, positive here. We have an electric field now flowing down through the material. What's going to happen to all those dipoles? Yeah. So now you'll have this nice uniform. This is kind of theoretical. I don't know how this applies directly, but now all the dipoles are aligned, and they'll have characteristic charges, right? All of them have positive, negative, they're polarized. So in the middle of the material, all of those forces, the positive and negative forces, will be canceled out, but you'll end up with a net positive charge up here and a net negative charge at the bottom. When you have two plates of positive and negative charge, what happens? They're attracted to each other, right? So you actually get a compression of that material. So by sending an electric signal in, now you have a mechanical result. We call that electrostriction, which I hadn't heard of before. So you can turn an electric signal into mechanical vibration, or vice versa. Like the material that's polarized, like quartz, let's say, you induce a mechanical stress onto it, and an electric signal comes out. So that's the basis of transducers. You are sending that signal to then generate a sound wave, and then you're sending it at specific time intervals so you have the frequency that you want. I think that's all I wanted to say about that. These can send information and receive information more rapidly than you'd care to probably think about. But notice, you might not be able to notice, this transducer has a curved face, where the other ones have a flat face. I have a transducer here for reference. That's a typical hand transducer you put on material, send sound waves through. I was going to draw something. Oh, so let's say, for the rest of the lecture, this will be a transducer. Anytime I draw it on the board, the X is a transducer. So if you were just send a pulse out, you'd have something like that, right? With a curved surface, what you're able to do is focus that beam so that now, if I can draw this right, you can look at a certain depth of interest. So that's what you're able to do with just a single transducer. And you can, we'll talk about methods, I think, right on the next slide. Perfect. So you can do something called through transmission, where you have a transducer on this side that's receiving, a transducer on this side that's pulsing. You're sending the sound wave through, receiving it in this one, monitoring how it changes, and if it changes, wondering what happened along the way. If there was something in the middle here, then it might reflect back and your signal would be lessened once you hit that spot. If there were a hole there, it might go through faster, it might refract in different directions. So this is through transmission. You have a transducer on either side. Now pulse echo is when you remove that transducer. Let's say you can't get to the other side of whatever you're looking at, which is often the case. If I wanted to inspect this table, I wouldn't really be able to shove my hand under there and have two transducers or anything. I would have to send it in, then when it comes to the back of the material here, what we call the back wall, there'd be another impedance mismatch, right? You'd have material here and material here, so you get a reflection coming back up. So you pulse receive, pulse receive, pulse receive, pulse receive. That's called pulse echo. Pitch catch is where, I already have them set up. You have two transducers, and you're sending with one and receiving with the other, still all on the surface. Okay? So this is what you do with a single transducer. And I like to think of pulse echo like when you're driving your car, close your eyes, you start beeping your horn, and you use the sound waves to echolocate yourself and know if there's a car close to you. So the same concept.
Texting?
Yeah. Well, texting you can do it verbally while your eyes are closed. If you yell loud enough, you don't even have to beep your horn. This is an example of through transmission. I think this is just a cool picture, but you have some part that you're inspecting here. You have these little water jet squirters, so they're using the water as a coupling medium because the sound's going to travel through water a lot better than it will through the air. So you have a transducer back here, one's sending, one's receiving. This thing can follow all the contours and it stays the same distance apart, and you can map out the entire part the whole time while you scan around. So this is just a picture, and all of these are ICO approved from Ken, so we're good. This is a system that this gentleman in the back actually designed, primarily, I believe. Two independent towers that move in conjunction with one another. So first it'll come in, it'll scan the part just to get its position, to know where everything is so it doesn't bump into it. And then it'll turn on these ultrasonic transducers and squirters and go around and scan every single millimeter of this part up and down. It'll do what's called rastering, kind of like mowing your lawn. You wouldn't, if this was your lawn, you wouldn't mow a strip, come to the sidewalk, mow a strip, come to the sidewalk, mow a strip. You go like this, right? So same thing on the part. To save time, you go over, 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 etc. Small displacements, move all around. That's a cool system. So these were single elements. Now we'll talk about phased array. If you have that capability with one transducer, what if we had more? Typical physicist question. What if we tried more power? What if we did lots of them? So you can have anywhere from 2 to like 128. There's probably more, but I think that's the largest I've ever seen, of transducers all lined up together. All right, and they'll be in a compact little box for yourself. But what you can do then is pulse them independently to then get constructive interference and get a desired wavefront. So all of those waves that you send out will propagate. If you look here, this is kind of a demonstration. It was an animation. Those little yellow dots, imagine them coming down, and then as soon as they hit the yellow rectangle, it generates a sound wave. So these two go together, those two go together, boom, boom, boom. Then you get this net resulting wavefront. So this is a focused waveform. Down there you can have angled. You can do a couple things with it, actually. Let's say you have, this is your phased array transducer now, instead of your single element. And you have that, and you say you have 64 transducers in there. You can fire the first 8 and focus them here. You can fire the, so 1 through 8, now 2 through 9, now 3 through 10, etc. And you can scan that way while you're moving, and this is a linear scan. This is great for speed because you can just go along. What you can also do is use all of them, or some of them, and step down through the depths by focusing on different depths. This gives you really nice resolution, really nice waveforms and pictures generated, but it takes a lot of time because you're going through every step there as you go down through the part. Then you can also do what most of us are probably familiar with. Say we focus over here, and then we sweep that. Right? So that is nice because you can cover a large area while this remains stationary. So your result will be kind of what you all are probably expecting, an ultrasound that you get at the doctor's office. The benefit to there is you have a stationary transducer sweeping out the area. You don't want to say, okay, hold still, ma'am, and then go back and forth for 25 minutes, and then just get a blurry picture of like a potato inside of it. You want the details right then, because the baby's going to move in that time frame while you're scanning. So those are different things you can do with phased array. Also, let's say we had, here's a material, we had a crack that wasn't necessarily right where we want it, perfectly parallel to the surface, we can then inspect that crack a little better by sweeping through it that way. So we have depth scanning, beam steering, and linear scanning. Another thing you can do with ultrasonics is a thickness measurement. Let's say, okay, we want to know how thick this table is. Well, you can take a caliper up to it and you can measure and say that's how thick the table is. But if you have something that, let's say, you don't know, you can't get to the other side or you can't get a caliper around it, how do you do it? Put a transducer on it, send a signal in, measure the time of flight that it takes for you to get your signal back. So, put the transducer on the material. Oh, first. And now we send the wave in, it echoes, it comes back. So you'll get a reflection off the first surface that you touch, right? You'll have some coupling medium in here so that you get a nice contact. You have a reflection there, and there'll be a time delay. Then you'll get a reflection off the back wall. Then a little bit later, you'll get a little bit of an echo, etc. There'll be a very specific time interval here. And I say, okay, slow down, physics breath. You have these time intervals, but you don't know how fast it's traveling, right? What's the wave speed in this material? That you can calibrate by, while you're making whatever parts you're interested in, you make a step wedge. Multiple known thicknesses you can measure with as many other methods as you want. You can use calipers, optical microscopy, anything that you choose to verify this is the thickness. So that then you can take your transducer and say, okay, it took it 3 milliseconds to go through that one, 6 milliseconds for that one, 8 milliseconds for that one, etc. You can get a calibration curve, so then you know your transverse, or you know one of the modes of your sound wave that's traveling through the material, you know one of those wave speeds. The trick is making sure that when you're taking the measurements, you're still normal to the surface, because as soon as you go off normal, now you're exciting more modes that you're not interested in. So for metals, this method works great because they're isotropic, they're amorphous, more homogeneous, and you get a really clean signal. You can get thickness measurements that are just accurate to tenths of thousandths of inches, whatever you want to be. But here with these composites, since you have those different wave modes, they're non-homogeneous, non-homogeneous, whatever you'd like to say there, anisotropic. You have to be careful because your surface won't necessarily be flat all the time. You might have a layer of material that's not carbon composite on the top and the back. So there's lots of considerations. So there's typically a plus or minus factor in there. You guys, oh, so celerity, I'll talk about that. If you guys use the letter C for the speed of sound, is because you're talking about the celerity, or the speed of light, sorry, the celerity of light, the swiftness of the movement of light. It comes from the Latin root, but also in materials, you have the celerity of sound in material. The root comes up in terms like acceleration, the swiftness of your change in velocity. In celebrity, a swiftness to fame, your quickness to fame. In celery, how quickly you want to eat something else. Same thing, shows up all over the place. So now we get into the cool stuff. Don't look at that yet, but it's nice. So let's go, oh wow. Let's go back to, how? Okay, let's go back to this example over here. Sorry. So, if you have, a material, we'll go back to this example here. You send a sound wave through, you get your front wall and your back wall, as we call it. Now that's just in one location, probing down through one spot. Now this material is composed of lots of those. So as you move around, now let's project this out into this direction. You'll get, let's say, another one here, another one here, etc. Now if you were to then, before we sandwich them, now we know we have like maximum amplitudes, right? We can assign those a color scale. We'll call this one 0 and this one 255, something like that. So your max amplitudes are now, all this is divided up into a color scale. You sandwich those together, and now you can look at it from the side. So imagine those waveforms, now you're looking at it from the top, and you have all of these maximum amplitudes that are combining along there, have the same value. And then here's a back wall, so this would be kind of like a step wedge. The thickness changes as you go through the material, right? But then you look here, and what happens? All of a sudden, let's say you get a wave in the middle there. You're getting a reflection off of something. So now you have things going on there, but not all of your sound energy is going to transmit through now because it reflected off, so you get these gaps in the back wall, and that can show you where these flaws are hiding. Same thing, I'll go to here, and then I'll go to some demonstration. Yeah, perfect. This is a kind of a top view of a similar material. You have different thicknesses. So the color scale on here is representing a time of flight, how long it took the wave to go through. So the longer it takes, you step through the colors. But you can see here pretty clearly there's something going on, right? So this is a standard that we made. You insert the flaws intentionally, and then make sure that you can detect them at different depths. You kind of develop the best way to detect these things. This up here is not necessarily the time of flight, but your amplitude, right? So it'll be just your an arbitrary scale in decibels versus your time, or in this case, your position, your stand direction. You can't quite see down here. I apologize for that because it's got a dark color scheme. But this is your So behind each of those, and still the resolution isn't great, but I think on the next, when I pull this up, you'll be able to see, you have these echoes. It'll hit that piece of FOD, whatever you're interested in, and it'll hit it repeatedly, right? So you'll get these repeated echoes down through the material. You have to be careful because sometimes you'll get reflections or refractions that start exciting modes in other places, and you get kind of a weird baseline background through your material. So you have to be aware of everything that's going on in there to make sure you're understanding your data appropriately.
Your prior slides showed reflections really well. Yeah, that
Oh yeah, oh yeah. So this is your back wall getting ping, ping, ping repeated. You can see that it's pretty uniform, and you know that, okay, that's the back wall material. That's your answer. Thank you, Ken. So now what we'll do, start there. So this is what we call an A scan. It's your simplest waveform, what you get raw out of the transducer. This here, we'll talk about it in a moment. And for this part, I might need to turn around and look at what I'm doing, because now it's over there instead of in front of me. So over here you have your A scan, your raw waveform like we talked about here. That's your front wall and your back wall. And we translate that into the B scan. Here, this is like a side view of the material, right? We're looking at an edge on, just a single thin slice of it. Now we combine all of those thin slices, look at it from the top, and that's what you have in that top, your C scan. And then you're able to slice through the depth of it in this direction by adjusting where you're looking at in the waveform, right? You know where your first one hits, and then you can slice through different times or depths. You can change it to be millimeters or times, seconds, whatever you want. So if you look where we are right now in the B scan, it's pretty clean, right? You don't see anything in the middle. You have a surface and a surface. The middle's pretty uniform and isotropic. So we have a front wall and our back wall. As I grab the cursor here, there we go. So I can slide through here, watch your A scan. Not much change there, right? That's pretty uniform. What if we then come down to somewhere, you can see the gaps in the waveform there, come up. Now what's that in the middle there? You get a reflection. And if you look then everywhere on your B scan, you can see, okay, I have something there. Let me move actually up here so it shows up on the A scan. Then look back at your A scan, nothing. And then you get a little bit, a little blip right there. You see that come through? And a bigger one right there, but that's near surface, right? You can see it kind of molds into that front wall waveform. And then if you look down at your B scan, you see, yeah, that's pretty near the surface. So you can watch the waveform as you kind of drive around on these parts to see what's going on. Right, so okay, this looks rather interesting. Now look at the B scan. We have flaws all across, and you can see those up there in your C scan as holes going through there. So let me think if I'm seeing anything else there. You can change, gates. We'll talk about that for a second. So we'll go to a front wall. Now if you look at your A scan, we've isolated that front wall, that first surface that we're interested in. We're saying, okay, we're only going to look at what's going on the surface. Right? So now this is a representation of the surface of the part. And as I move around, you can see all the surface flaws in your B scan down at the bottom, but there isn't much going on, right? Now you can change that gate to, let's say, internals. I think Okay, so now we're only looking at this area between the first surface and the back surface, front wall, back wall. And now you can see pretty vividly the flaws in that material. If we were to come over to here and then slice up, oh, not on this one. You can see that flaw pop up right in the middle, and it's so pronounced on this C-scan because we're only interested in that middle range, so your color scale now is showing you a lot more information. So you can use these scans to then inspect every single part that comes through. The application is you decide, okay, we're building this part, and we know it's in a clean room, but all these things are potential candidates for something that could get into the material. So then we make something with all of those in it, and we try and develop a method to detect all of those things that we're concerned about. We make sure we can prove we can detect flaws this big, at this depth, in this material, in this part, reliably with confidence of whatever. And then the goal is that you don't find any of those in your parts once they're being made, but you scan every part that comes out the door. If it's in there, say, okay, we're going to have to trash this one, we're going to have to inspect it a little more, we do different scans. But that's the ultimate goal, is flaw detection in this aspect. You can also do, like I said, failure analysis. You can use other methods other than ultrasonics. We can do thermal imaging, where you flash heat onto your surface and then have an IR camera and see how that dissipates off of there, and you see the differences in material, and you can kind of get an idea. You can do shearography, where you're, I won't talk about shearography. You can, laser, we call it laser UT, I think, but you're using a laser instead of sound waves, and also get an idea of what's going on the surface and inside. And I think that's all I have. So 5 minutes for questions.
So before we do questions, I want to make sure everyone knows that next week we have our last talk booth, where our resident chemist is going to come and tell us about the physics of her chemistry. Make sure you come back for that. Okay, so question. Yes?
Hey.
So if you want to tell us about shearography, will you tell us about shearology?
No.
Okay.
Next. Dr. Soul?
It's been a long time since I've played with NDT, but my recollection is maybe...
Non-destructive testing is what NDT stands for. Sorry.
The critical angle 2 is total internal, is angle 1 is total internal reflection.
Okay.
And critical angle 2 is the acceptance angle into a waveguide, if I'm remembering that correctly.
Okay. So what, did everybody hear that?
Okay.
So your critical angles, okay, we're good. You know what total internal reflection means? Used in fiber optics, super handy. Next question. Got everybody's, yes.
So far, everything you've talked about has been for the longitudinal aspects.
Yes, I didn't go into plate waves or guided waves, other than describing them.
Okay, but those would be important also because
Yes.
you can have other sorts of motions in there.
Yeah, you always have to consider all those other motions.
What they're going to talk about.
Well, I think, but
We did
one
mention
case-
SHM at the first.
Pardon?
The SHM, the structural health monitoring.
That was also
Yeah.
released.
So I was just
Um,
giving you an example of something.
Oh
that
yeah,
Pat
so
talked about.
that crew containment module that we brought up earlier, that was using plate waves to detect impacts, basically anything that anything you're not interested in happening to your case in transportation if it were to fall off something. So that's only focusing on plate waves traveling or surface waves traveling then to those phase array detectors. Did I answer a question there? Was that
I think so.
another? Okay.
Yeah. As well as you're going to, yeah.
Thank you.
Or as well as you'll be allowed.
Could we look back at the using the water as the method of transmitting the signal through? So where are the transducers in this?
There, so this is hollow in here. You have water coming in there. Transducers are further back. Then you make sure that you have a laminar flow. You don't have bubbles and things going through there. So you can then send the sound wave out, centered through the water, and then through that stream that's coming out of there. And then it
Okay.
hits the surface and then gets received on the other side into another stream
So
of water.
you've got, because it kind of looks like, I can't really tell from the contrast, but so you've got two water jets essentially.
Yeah, so
spraying
here,
against
this
the
is a water
surface.
stream, this is a water stream. on either
And
side.
that doesn't, and because the water is going to produce a completely different frequency than what you're using with the transducers that's in the pump at all, right?
It's not the frequency, it's the fact that sound travels better in water than air. So air attenuates sound fairly quickly, but water, so your
Think
sound
being under a
waves
pool.
don't attenuate, and then you can, unless I'm going the wrong way in your
Yeah.
question there.
No,
You flick the ladder, you can hear it on the other side of the pool. You get out of the pool, somebody flicks the ladder, and you have no idea how.
I was just meaning, and there's no interference caused from the water's jet against the material.
No.
So for that, the crew,
Yeah.
the crew module, that array, could you use that to monitor, monitor hull integrity in flight? If you put it in space, could you use that
Yes.
to tell if you've been?
I believe so. It depends on what it is, because if it's in a rocket motor, I mean, you're not going to have all this propellant and these transducers inside of there. It'd be
Yeah,
pretty
right.
But yeah, and something like that, yeah, you could use it to monitor in flight, like, oh no, we just got hit by debris. I think you'd know if you were in the spacecraft, but,
I'm talking like the small.
oh, cracks and things,
Yeah, or small impacts that
Yes.
maybe you don't notice, but when you're.
yes.
Rehab.
Yeah.
Yes, there's
An
a example
crew
of this,
damage.
yeah.
Challenging.
No, yeah. Yes.
Other questions?
So, you made me realize something I thought I'd always understood.
Uh-oh.
So piezoelectrics, which I thought I'd always understood. I can understand you apply an electric field, polarize the dielectric, and you have some shape change.
Yes.
So why is it that it does work the other way? You do something physically, why should that change the polarity of the...
I was thinking about that, because it seemed like the materials that needed to, the materials that would emit an electrical signal once compressed were permanently polarized, and you would have to have two different materials in there. Now I'd be curious, this kind of side slice, where did it go? Sorry, that side view, I know you have a backing material and you have your piezoelectric ceramic in there as well, but I don't know if it's the same material that's both transmitting and receiving. That would be, I've never sliced one open personally, and I don't know any close friends who have. I know.
Do some NDT to it.
You have done this in the mechanical spectroscopy of concrete.
Yes.
It's the
They were the
stimulator, the transducer that stimulated the wave, and the receiver were identical devices.
Correct. But I'm wondering physically why that would be the case. If they're not polarized, then you induce a mechanical stress. How that would then generate an electrical signal.
I forget. I think it's because they're crystals. I don't remember the details inside of it.
It's the same element as pulsing.
If in the unit cell of the crystal, the center of positive charge and the center of negative charge aren't coincident, right, or separated, then any change to the unit cell changes the dipole.
Solid state is so cool.
You're going to take the course after you retire.
Yes.
I am.
Other questions?
I-
Oh, we'll do two.
With my 3D mindset,
Okay.
I noticed that you have lots of 2D images to try and show the data.
Yes.
Do they have a way to
They do. I don't think I have that capability right now, but yeah, there's software that we have available where you can do a 3D rendering, and then you can kind of dive through it, slice through whatever you can do. But yeah, then you just compile all the 2D images.
you can see.
That's really cool to see those. And those, your depth scanning of phased array will produce the best 3D images because you're getting information everywhere, right? Instead of just collecting it as a whole. There we go.
So, in the back room, we've got this demo with this eyedropper in the material, and you seen this one? Oh.
It's cool.
Yeah, we'll bring it out.
An eyedropper?
So it becomes invisible. The liquid, the eyedropper in the liquid becomes invisible because it's index matched. And I'm wondering if there's a particular, are there any defects you're aware of where there is no impedance
Yes.
mismatch and they're invisible?
And that's when you have to use those other methods. When you know, like, okay, we put something in there, it should be there. We're not seeing anything. That sound wave is just going right through. It doesn't even notice that it's there. Then you have to do other things like that.
Yeah,
So maybe then, if you flash it with heat, it might have different thermal properties.
Ah, okay.
Even if it's invisible to ultrasonics, there are other methods that you might be able to use to detect it. So that's when you start investigating. And that's why I like what I do so much with these guys is it's never the same thing every day. You're trying to figure out how you can solve this problem. Oh, yeah, so you guys can see that. There's a glass.
No.
Oh, no. Do I squeeze it? Oh, that's cool. Okay, so you can see it from up there, and then it disappears, right? Because your index of refraction is matched through the material, whatever substance they put in there. It's the same as
So most of it is hiding up in the cap and you're shoving it down.
That's the trick. Is that everything? Oh, so.
One comment,
Excellent.
and that is for any physics major, applied physics major. NDT is a tour de force of applications of physics combined with Sherlock Holmes. And it's a hoot. It's just absolutely fabulous. It's a really fun application of all aspects of physics. It's cool.
Yeah, I completely agree. I would recommend it anyway. I knew nothing about it going in other than basic physics and you learn principles.
Any last question? All right, let's thank
Thank
our
you.
speakers.